the seminar for the quantum group here in the CMS, which the organisers have kindly included in the program here at the Newton Institute, because we thought it would be of interest to many of the attendees here. It's my pleasure to welcome Barbara Terhal from Aachen University, who will speak about new circuit-to-Hamiltonian constructions, or different circuit-to-Hamiltonian constructions, and their application for QMA.
Okay. Yes, I'm happy to be here for this week. Originally I wanted to talk about something that would fit much better in the quantum marginal workshop. But I'm also quite eager to talk about this, although I have to confess, as you can see, it's work in progress. We're not quite done, and we have some hard mathematical problems still to solve, but I hope I can make a convincing case that this is interesting for quantum complexity theory, and interesting mathematics also, because I think many people have interest in mathematics here. So this is work with my student, Nicolas Brugman. So I will first talk about what the circuit-to-Hamiltonian construction is, and what its uses are, why it's interesting, why it's sort of fundamental in my mind, and then we'll talk about the different proposal of such a circuit-to-Hamiltonian construction and the analysis that we've done so far on this new construction, or new-old construction. So what it is, it's a construction due to Feynman that was first used by Kitaev, and it's a way of taking a quantum circuit or a classical circuit, you can also take that, and map that onto the ground state of a Hamiltonian in the following way. So a circuit, of course, has gates that turn on and off. So it's generated by some time-dependent dynamics. And what you want to do is you want to represent the output of the circuit as the ground state of a Hamiltonian that is time-independent. So well, why is this interesting? Well, this could be a way of realizing a quantum circuit. So we assume that the circuit has, this slide just is about the basic construction. So the circuit has n qubits, and it has a bunch of gates, just U1 to UL. I don't care what they look like in detail. But so given that, I'm going to write down a Hamiltonian that looks like this. First, this Hamiltonian acts on the qubits in the circuit, but it also acts on another additional register that I define, which is called a clock register T. And this this time, runs from 0 to L, which is the time after all the gates have been done. And the circuit Hamiltonian looks like this. So it's something where if the clock jumps from time t minus 1 to time t, the gate ut is done, which seems very natural, because that's what happens at that time. There's a Hermitian conjugate, which would reverse the action. And then there are some terms that make this Hamiltonian positive semi-definite that are not that important in this construction. One can check, I'm not going to show this, that this Hamiltonian is defined such that the ground state of this circuit Hamiltonian is what we call the history state of the circuit. It's not the output state of the entire circuit, it's a superposition over all times, and given that time, it's what you get if you put, so let's imagine that the input to the circuit is the state psi, and then the action of the circuit is doing the gates U1 to UT, and you have this superposition over all times. So this, of course, is in some sense not a unique ground state, because I can input any state. But modulo that freedom of inputting a particular state, it is the unique ground state. Okay, so I want to say a few more things about this Hamiltonian, because we can get a little bit of intuition for it. It's a very simple Hamiltonian. You can see it if you don't think about the action of the gates are just the identity gates. You know, what it is just some particle, a kind of a clock particle, hopping on a line. So this particle hops from position t minus 1 to t, and the gate ut is executed, or the inverse happens. So that's why the spectrum of this Hamiltonian is actually very simple. Because, well, of course, we have these gates ut, but you can also show that you can unitarily relate this this Hamiltonian to Hamiltonian, where these gates are just identity gates. And then you just have a simple 1D Hamiltonian of a particle hopping, and we know what the spectrum is. Okay, so one other feature of this history state, which makes this a useful state, is that if we were to measure this time, of course with equal probability we would draw some random time. We would get some time t with probability 1 over L, probability L 1 over L plus 1. Yeah. Now if we want, of course, to get from this state, we want this state to capture the whole history, but also particularly the output of the circuit. So what we can do is we actually, when the probability of getting the output state is only 1 over L plus 1. But we can boost this by modifying this construction and taking a lot of identity gates at the end. So that's a small thing, it's a bit of a side note, but if you take a lot of extra identity gates, then you say, well, I don't care whether I draw the final time or any time in that final part of the history is good, because in this register I will then see the output of the circuit, because the only gates that are still happening are the identity gates. Okay, so now so one can read out the answer of the computation of the circuit from the history state. Then furthermore, there are what the people have done is they have discussed how to realize this clock register, because now this is just some register that goes from state t minus 1 to t. So how I could realize this, for example, by having what we call a domain wall clock, by represent time in the following way. So this is the time, this is a register of length the total time, and when this sort of domain wall is here, it's this particular time, or we could realize the clock in this way. And the reason to do that, I'm not going to go into this in my talk, the reason to do that is to make this circuit Hamiltonian and Hamiltonian act on a few qubits. So if you see the original, this is a gate in my circuit, assuming that works on 2 qubit or 3 qubits. This is in principle something that acts on log L qubits. So there are realizations of this clock that make this act on 2 or 3 qubits. Okay, but that won't concern us too much in this talk. So what is nice about this is a very simple Hamiltonian. So the spectrum of the circuit Hamiltonian, like I said, is actually independent of what gates you do. You can do a unitary transformation that transforms that away. And we know the spectrum of a particle hopping on a line, which relates to these momenta. So the energies can be labeled by the momentum k, and k is 0, corresponds to the ground state. And the gap of such a model goes like 1 over L squared, the length of the chain. Okay, so that is a standard construction that people have used a lot. Now let's talk about what is the use of this construction. Why is it interesting? So it was first used, so it was first sort of defined by Feynman and then used by Kitaev for what we call the quantum Cook-Levin theorem. And that is a proof, so that pertains to the class QMA that I think we've heard discussed in this week. So QMA is the quantum equivalent of NP. And like for the class MP, you want to know what problems are QMA complete. And for MP, this is proved by the Cook-Levin theorem. That people show that the problem 3 set is NP complete. And so for the quantum Cook-Levin theorem says that to determine the lowest energy, the ground state energy, of some n-qubit Hamiltonian with high accuracy, 1 over poly n accuracy, is QMA complete, is hard for quantum computers. I'm not being very precise about what I really prove, but it shows that in general determining the ground state energy of a Hamiltonian is very hard, even for quantum computers. Okay, so we won't be, so this is a fundamental result. And of course you'd like to show that very physical Hamiltonians are QMA complete. fermionic Hamiltonians in 2 dimensions and so on. So there's been a lot of work on trying to prove that various Hamiltonians are QMA complete. So finding the ground state energy, determining ground state energy is a hard problem, even in one-dimensional quantum spin systems. Now, I just want to give you an idea of how this this Circuit-to-Hamiltonian mapping is used. So what you do, so we have a mapping from a circuit to a Hamiltonian. And what do we know? So what we want to show is that any problem in QMA can be mapped onto the problem of determining the lowest eigenvalue or lowest energy of a Hamiltonian. Yeah? And what do we know about any problem in QMA? Well, it's a problem in QMA, meaning that if the answer to there's a verification circuit, so if the answer to the problem is yes, there's a verification circuit which will output 1 if it gets a valid proof, proving that the output is 1. And at the same time, if the answer to the problem is no, then this verification circuit will output 0 with high probability. So we have that verification circuit. So you're going to construct a Hamiltonian that basically verifies the action of the verification circuit, that checks that the inputs are correctly, not the proof, but the inputs of the verifier, and that checks that this output bit is 1. And so the idea is that if the verification circuit would output 1, then this Hamiltonian has a 0 energy eigenstate. Meaning there's a state that has 0 energy with respect to the circuit Hamiltonian, which is that history state, that has the correct input bits, some part of that state psi, and that also corresponds to the right output, that output being 1. Okay, so I don't want to go too much detail about this. So what you also have to show, of course, that if this verification circuit, if the problem is no, and the verification circuit outputs 0, then that this Hamiltonian has to have energy away from 0. Yeah? It has to have high energy. And there has to be some kind of gap, and this gap is like 1 over poly n. But and so you have to look at the lowest energy states of this H. And this requires also looking at, so let me just say this. In order to do this, you need to know properties of the gap of the circuit Hamiltonian. Okay, so maybe, I don't want to go into too much technical detail, but I just want to provide a motivation why we're interested in looking at properties of the circuit Hamiltonian. Okay, so other uses of the circuit-to-Hamiltonian construction is the model of quantum adiabatic computation, where you say, I define a circuit Hamiltonian that's actually a function of time in the following way. At time t is 0, I take my circuit-to-Hamiltonian, and I just take all the gates to be identity. The spectrum of that Hamiltonian is the same no matter what I set the gates to be. So it has this 1 over L squared gap that I mentioned before. And at some final time, I set the gates to be the final gates. And then, if these are elements of some SU2 or SU4, I want to do a smooth interpolation of these set of gates, all being the identity, to these being some other bunch of gates. And I can do that. These are just, Lie groups, they can be smooth deformation. And when I do that deformation, the spectrum of these Hamiltonians don't change. And you can show that if you want to do adiabatic computation, if you specify a path of Hamiltonians, so a time-dependent sequence of Hamiltonians, and all the Hamiltonians on this path have some 1 over poly n, some gap, n being the number of qubits or the size of the computation, then you can realize this efficiently. Okay, so that's another motivation to use this circuit Hamiltonian to do universal quantum adiabatic computation. So instead of running a circuit to encode a computation in the ground state of my circuit Hamiltonian, start with sort of a trivial Hamiltonian and gradually let that evolve to the final Hamiltonian that encodes the answer of my computation. So another way of using, I think also this Feynman mentioned this when he defined this, is to use this just as a quantum walk on a line or a circle. So in there, you don't start any ground state. You start in the you start to walk in the t is 0 state, and you evolve. So that's of course, or you start a little wave packet there, localized at time t is 0, and you evolve with the circuit Hamiltonian. Now, if you evolve in a particular, so you want to evolve for some random time, and you can prove then, depending also on the gap and so on, that you will sample from states in this uniform ground state distribution. And you can do that in 1D, where this is the original time, and this is the final time. And you can also do it on a line, on a circle. So there's a way of modifying this where you apply the gates, you have a circuit Hamiltonian which applies the gates in two directions. Okay. Okay, so that's on the use of this circuit to Hamiltonian mapping. So now I want to go to a different construction. And so there's a construction in 2007 proposed by Mizell, Lidar, and Mitchell that they of a particular fermionic Hamiltonian that they proposed would realize adiabatic quantum computation in this manner that I just sketched, where you had a circuit and you encode the gates in a fermionic Hamiltonian in this case. And what is nice about their model was that it's kind of physical, because it's a fermionic Hamiltonian of a two-dimensional system, and there are quadratic terms, so hopping terms, and there are some quartic terms, but they're also local. So of course, if you have, it's not a Hubbard model, it's not that simple, because it also has to encode the unitary gates that you're originally doing, but it has a certain physical appeal. Okay, so how does this, I'm not going to write down the Hamiltonian, I just want to tell you a little bit what it looks like. So the way the way one defines this Hamiltonian is that in your original quantum circuit, you had a bunch of qubits. And let's assume, and I'm going to come back to that in a moment, because I'm going to assume that throughout my talk, that my quantum circuit is consists of nearest neighbor gates on some 1D line. I can always map any quantum circuit on such a quantum circuit. And that's why we'll get a two-dimensional Hamiltonian. But so a qubit in this quantum circuit, and this circuit has depth d, say, we will represent by 2d plus 1 fermionic modes. So what we do actually is that we have fermionic modes I going from 0 to d, which is sort of like the time evolution. And there's an internal state which I could call a spin at every point in time. So the idea is a little bit that the internal state is the state of the qubit. Well, that to represent that as a spin state is very natural. And the time evolution, the updates on that state, are realized by these fermions hopping forward. So if I now, imagine now, in my original circuit, I have only one qubit and a single qubit gate. So how I represent that in my circuit Hamiltonian, before I had a different clock, a clock for everybody, for all the qubits, and then the gate is applied and the clock is moved. Here I just say, well, I have a term where the fermion hops from site, say, from mode, from place 0 to 1, and the particular unitary gate is realized on its internal degree. Yeah. So but then of course you can do a single qubit gate like that. But a 2-qubit gate, you say, well, okay, what I need to do, I need to then make sure that both fermions hop. Yeah? So the pair of fermions have to hop together. They have to both update their time, because you could say these fermions, where they are on this track, they sort of, every qubit represents to a double, well, it's sort of a track, and where they are represents their time, how far they have advanced in their gate action. So the 2-qubit gate, and it's actually only for controlled unitary you can do this, is represented as a pair of fermions hopping together, and their internal state changes depending on the spin state of the other. Okay, so now the motivation for us was to analyze their construction, because they claim their model has a nice gap. They claim it can be used for adiabatic computation. I did the gap. They're very brief about how to bound this gap, and I think it's a highly non-trivial problem to actually do this. So I was a bit hesitant that this was rigorously done. Furthermore, I want to see whether we can use this construction for QMA. Yeah? So this is the starting point of our analysis. And now I will sort of forget about this hopping fermion model, because I'll give you actually, no, not yet. I'll give you a construction that is, let me just double check that I have that. Oh yeah. Oh yeah, yes, that's coming that. I'll give you a different construction that is unitarily related to it. Okay, so my personal motivation, that may be too ambitious and may not be, turn out to be, this whole construction may be useless, but I can at least say it, what questions I have concerning this. So in the Feynman construction, you have your original circuit, yeah? The circuit has, say, some geometric locality, meaning that it corresponds to a circuit of qubits interacting on a 1D line or 2 dimension. It has a certain depth. Huh? And these properties, we believe, should influence the output state of the circuit, how entangled it is, whether it satisfies an area law, and things like that. But there is also a relation to, we also believe that so what we want to do is we want to have a circuit-to-Hamiltonian construction which preserves some of these features of the original circuit and expresses that in terms of features of the Hamiltonian. Meaning, whether it has a gap, what are the excitations, that depends on the depth, on other geometric locality of the circuit. And the point of this Feynman-Kitaev construction, it only depends on the total number of gates in the circuit. So you drop these features. Another motivation is that can we find or formulate a physically natural, something that you could realize physically, say 2D interacting fermions, universal quantum walks. So this has been done, for example, by, fairly complicated construction by Childs and all that. But it seems that also the construction by Mizell et al. Could potentially be used for universal quantum walks, but then one has to prove some properties of this. How quickly do you sample from the ground state distribution that relate to the gap, and that wasn't done properly. So they're sort of a candidate. And then the other motivation is to prove QMA completeness for 2D interacting fermion models without using perturbation gadgets. Okay, like I said, we'll only consider 1D quantum circuits. So that's my 1D quantum circuit. I have n qubits on a line, and they just undergo 2-qubit gates. And I will assume a periodic boundary condition in this direction. So we have this sort of alternating structure, and I have some depth d. Yeah?
Do you understand that the number of fermions is fixed in the whole circuit? The number of fermions is fixed.
You mean to this Mitchell, yes. the Mizell model?
Yes.
Yes, they have one. So okay, that's right. Yeah, I didn't say that. So for every qubit, you only should have one fermion. So for adiabatic computation, it's not a problem because you just start the state with a single fermion on a track, and these fermions never hop to the track of another qubit, so to say. But for QMA, this is a problem because it's a very non-local constraint. If you have to put this in, you have to. So there are other ways. Yeah. This is the answer. Okay. Okay. So I'm going to do a circuit-to-Hamiltonian construction, particular to 1D quantum circuit, but you can also generalize it. But just the mathematical problems gets harder. Okay. So nearest neighbor interactions. There are 2 qubit gates. Okay, so now I'm going to describe a Hamiltonian that you can prove is unitarily equivalent to this model of Mizel et al. That I didn't formulate. So you can't verify this, but I think this model is more clear to state what actually you do. So because what it is, it's instead of having one clock for all qubits, you actually just have one clock for each qubit. Yeah? So I have a qubit, so I have my quantum circuit, and now I define a bunch of clocks. For each qubit Q, I have one clock, and this clock runs from 0 to D, to the depth of the circuit. And now I'm going to, in order to define the circuit Hamiltonian, I do that according to the following procedure. If I have a single qubit gate U on the qubit Q, then I would do the following term, which is very similar to what I had before. I advance the clock of that particular qubit from S to S plus 1, and I apply the gate U on that qubit. And I have the Hermitian conjugate of that, and I have these additional terms like I had before. Now, if I do a 2-qubit gate, on 2 qubits Q and P, then I have here, I ask that the times, actually this should not be C, this should be P. The times of these 2 qubits should be the same, and then they're both advanced. So this term only does something non-trivial or non-zero if the times of those qubits are the same. And then I have the Hermitian conjugate, and I have again a term like that, which turns out to be a little bit more non-trivial, or it has to be kept around in this analysis. Is that clear? Okay, so let's just get a sense of what that Hamiltonian would do if I would start the clocks of all my qubits over here. So all the times are the same, and they're all 0. Yeah. So if I have the circuit Hamiltonian act, the times of these qubits could advance by 1, both. This could also happen, or that could happen, but by the action of the circuit Hamiltonian once. If I apply the circuit Hamiltonian, so these are just one term in the state that I would get. Yeah. Of course, I could, if I would apply the circuit Hamiltonian again, I would get something like this, etc. So, okay, what I want to say, this is a bit maybe too suggestive. What is clear is that if I have a configuration in which the times of these qubits are just random, very asynchronized, then the circuit Hamiltonian would not do very much, because it only has some action if there are some qubits which have nearest neighbor qubits which have the same time. But of course, if I would start the computation in a state where all the qubits have the same time, so a synchronized state, then the Hamiltonian would preserve. It would not keep this qubit synchronized, but it would preserve a space of what I call proper time configurations, and I could call them space-time configurations. That's a little bit suggestive, but it's not. I mean, nothing is moving in this model, so it's just that I could look at space as this is a line of qubits, and I could say, well, what? There's a subspace of all possible time configurations, and what characterizes the subspace? And what it characterizes, you could say, well, the times of these qubits, you could say that's either they're space-like or light-like separated. What I mean by light-like is that you could have a configuration like this, where these are synchronized, but this guy can be there, and waiting there until this guy is updated. Yeah? And the same there. What you cannot have is something where this qubit, there's a blue dot here, and there's a blue dot there. That's not allowed, because that means that one qubit has gone through the gate and the other one is not. That's never a configuration that I'll get from applying my circuit Hamiltonian. And there are also these light-like, I would say, this is, if I had a periodic boundary condition in time, then I could have a fully light-like configuration where this is always goes on, and I have a periodic boundary condition coming back here and so on. And the energy of that configuration is 0 with respect to this Hamiltonian, because it doesn't act anywhere, because nothing is synchronized. But if I have a beginning and an end of time, the beginning and end of the circuit, which of course I have, then at some point here, these qubits, they will be synchronized, meaning that any configuration, there will always be qubits that are synchronized, and the configuration will move to a new state. Okay, so it looks nice. Okay, so now, but the work that we have to do is not so easy. So a few comments. So what I want to use this to maybe for quantum adiabatic QC. So you could think about realizing the clocks of these qubits, everyone their own clock in some way. And then you want to consider the gap of the circuit Hamiltonian in the proper time subspace. And what I need to do is I need to prove that this gap scales as 1 over poly n and comma d, some polynomial in n and d. Because d, the depth of the circuit, if this is is typically poly n, so this is entirely some poly n. But I'm also interested in, say, maybe looking at a very low depth circuit and see how things scale then. But this, okay. So for QMA, one has to do one has to. One has to do a bit more. So what you want to do for QMA is you want to write down a Hamiltonian, which part of it is the circuit Hamiltonian. But it also puts penalty if the input is not the right input to the verification circuit, and if the output is not 1. And it also has to put a penalty for qubit times which are not proper. And you can do this, there's a way to do this in the original Mizell model, which is really local, so that is not really a problem. And this is some other term, we don't worry. But what I want to talk now is actually to lower bound this gap. That's the, maybe I'm running, are there questions here? Okay, so, now, and this turns out to be, I think, a very nice math problem. Maybe a little bit too hard for me, I don't know. But so if you want to solve it in its full extent, so you have to be clever. Actually, yeah, okay, so you can show that in this proper subspace, so this is a subspace of time configurations that are space-like or light-like separated, this circuit Hamiltonian is unitarily related to the one with identity gates on the qubits. So forget about these gates on the qubits, it's just about the spectrum of the circuit Hamiltonian in this proper subspace. And you can show, that's very simple, that actually the circuit Hamiltonian is a Laplacian on a graph. For the Kitaev model, it was just a one-dimensional, Laplacian on a one-dimensional line, where the vertices are just these times. But now the vertices are a vector of times. It's a time configuration. It's actually a string. It's a whole configuration. So I have vertices that are these proper time configurations, and two vertices are connected by an edge. If the Hamiltonian lets me go from that time configuration to the other one. Now, okay, so you can show is the graph is connected, and it has a unique zero eigenvalue state, and that's the history state. And the history state in this case is not just the superposition over all synchronized times, it is superposition over all, proper times. Now, this is not a simple some problem. This is because this graph is not regular. So what you want to do here is to try to relate it to bounding. There's a lot of work in computer science about bounding mixing times of random walks on graphs. But let me first say a little bit about what the graph and what the actually there's a nice physical problem that relates to this, and I want to show you that. And so I want to go from time for configurations. So these time configurations in this representation, they go like like these kind of things. Yeah. But I can also represent it differently in the following way. And this is not so hard. So let me, every gate, 2-qubit gate, I will associate with that a plaquette or an Ising spin. And the Ising spin is either up or down, meaning kind of that the gate's been done or not, right? Of course, that if I have a configuration like that, it corresponds to a certain bunch of gates have already been done, and the gates on the right, they're not done yet. Yeah? So then this time configuration is like a domain wall in this Ising model. So these are the Ising spins, and so here the spins are in this area. The spins are all down, and here the spins are all up. And so this particular, the times now, if I represent each gate as a little plaquette, then I have to associate these times of the qubits with points on the edges. So this is this time, and this is not a one-to-one mapping, just an example of a configuration. And you can see that what it means to, let's say, for example, I say, well, I have this configuration here. If I look at that as a domain wall between Ising spins here and Ising spin there, you see that without the length of the domain wall is the energy. So I can change this domain wall by sort of going here. By flipping this spin to be up, then the domain wall will go here. And that doesn't cost any energy because the length of the domain wall is the same. So this process of this gap with the Hamiltonian, the mixing time, relates to actually the following model. I have a ferromagnetic Ising model on a cylinder, and I put in a domain wall, say some of them, and I want to know at 0 temperature how quickly this domain wall diffuses, how it can be found anywhere. Okay, so you look at some literature, and I didn't find this not, because typically they look at non-zero temperature. So if you had non-zero temperature, there are fluctuations here where you have little islands and so on. But here I'm really at the T0. Okay, so that's one representation. You could also say, well, what it is, it's a string on a cylinder, and it's the diffusion of this string, right? It's just how this string is connected and can't stretch, and it's how quickly this diffuses. Now, I'm going to say something at the end, but you can believe that the efficiency, how quickly it mixes, is not going to be exponential in this length or that length. This length is the depth of the circuit, and this is the circumference of the cylinder, is the number of qubits. You would not expect this, okay? So, all fine, but of course I'd like to get a number. I'd like to get, well, not a number, but I'd like to get an expression for this gap. Yeah?
Is there any way to see this as a random walk?
Yeah, well, it is a random walk. So what the random walk, so you have a configuration, which is one of these things. And then one step in the walk is where you just have, this little update. Yeah. And everything where I have these kinks in that model are updates, because these kinks, so in this new representation, this is the fully, so this was the fully synchronized configuration before, and that gets mapped onto something this. And if I have these kinks, they can flip this way.
So basically, the process could be thought of as inserting peaks into this. So flipping. So
Well, you just flip these things. So you go from this. The moves are this goes to this.
you
or this
probably can prove that this is rapidly mixing.
What?
You probably can prove that this is rapidly mixing.
By what technique?
Statistics of dick walks.
Well, the dick walks are on these are the boundaries. Yes.
Yeah.
Yeah.
And then-
But I mean, okay, yes. But maybe we should talk about this afterwards. Because indeed, the point is that if the string is on the boundary, it corresponds to a dick word. So the thing is that you clearly see if you have such a string, it's very simple that at every point in time, how many configurations there are, well, I can just go two ways at every step. But if I'm at the boundary, there's a boundary here, because the circuit has a beginning and an end. If I don't put any periodic boundary conditions there, then I cannot go beyond the boundary. And then instead of you get these dick words. Okay, so I want to use yet another different representation, which seems also very simple, and that is actually useful, and it brings us to some Heisenberg model. So I want to represent my time configuration. I can also represent it as follows. Yeah. So the times are these points, but I can represent this kind of string as saying, well, I take, say, for my first qubit, I take some point h. Yeah. And then I look at deviations from this h, yeah, which can be either this way or that way. Yeah, at every point, this way or that way. So plus minus, so that's a spin. Yeah. So I can represent it as an h and then n spins, which can be either up or down, yeah, 1 or 0. If I do this on the cylinder, there's a constraint that the number of up spins must be the same as the number of down spins. Because this has to wrap back to itself. And I can express my Hamiltonian just in this representation. But it's the spectrum is completely identical. So now what I'll do is I will choose, for simplicity, I'll just choose a periodic boundary condition in time. That is not, for QMA that gives some problem, but for, so if the D is much larger than N, this is quite reasonable. But let's just talk about that. Hope I haven't lost everybody. Okay, so I just want to get an intuition. What model, if I want to write the circuit Hamiltonian in this representation, what kind of model do I get? So there are two things. There's the H, and then there's the spin. Yeah? Now, if I do a gate, or not a gate, but just a move in the bulk, which I described as flipping this thing into something like that, or this here, yeah? You see, that's just a flip, right? If this is, I don't remember what I called this 0, and this is 1, then this configuration will afterwards be 1, 0. So it's a spin flip. 0, 1 will be mapped onto 1, 0. But if I'm in a 1, 1 configuration, I cannot move, or 0, 0. So that, and now the thing is, of course, if at the boundary, there's something special happening, because if this thing is moved at the boundary, I also move this boundary point. So I go from a configuration, say h of 1, 0 to a configuration h plus 1, 0, 1. So I do a spin flip and I update the depth counter. So, okay, so another way, okay, so you can show that the circuit Hamiltonian is a Laplacian on this graph, which the Laplacian graph is a diagonal matrix, a degree matrix, minus the adjacent matrix, can be mapped onto something like this, or it's just equivalent to a model where this represents the degree matrix, and this represents the adjacency matrix. And the thing is that there is no effect of the counter except in the boundary term. So there's this boundary term. This is C dagger here. So, so two comments about this. If we drop the counter, this is this depth clock. This is just a ferromagnetic Heisenberg model here. So if I fix this boundary, I just have the dynamics due to a ferromagnetic Heisenberg model, but it's in a sector where the number of up spins is the same as the number of down spins, which is not the usual model. Usually you're just in, well, otherwise it's trivial. But you can also see this as a different circuit-to-Hamiltonian construction, where I just say, because you can actually add, these gates, you could add a unitary, well, maybe I'll skip that, but this gives rise to, a construction that's different from this Mizell thing that could also be used for realizations. And that construction uses a depth clock. So there's only one clock, which is only the depth of the circuit. And of course the point is that these gates, it doesn't matter in which order they happen. So that's why you're allowed to do that. Okay, so now, so the connection with this Heisenberg model, but it's not the regular Heisenberg model because it's coupled, the boundary, it's a Heisenberg model coupled to a boundary, but of course it's the only, this boundary, this term is actually translationally invariant because I've put on boundary conditions. So I can just write eigenstates for this boundary. These are just plane wave states with a momentum. And then I can look at the spectrum of the circuit Hamiltonian. It's actually the union of spectra of a Hamiltonian labeled by the momentum, which is the ferromagnetic Heisenberg model in the sector where the total number of spins, the total z spin is 0, equal number of up and down spins, plus some boundary twist. So I've looked at later, there's some twist. So this is the boundary thing. For k is 0, this is 0. And this is not, okay, so so now you can show, if you want to find a gap, you have to do two things. You say, well, okay, I have a gap in the k is 0 space, but I can, of course, it's very clear that for k is 0, the zero momentum state of the depth clock is the ground state of the Hamiltonian. So then you say, okay, first excited state, where I can find it? I could find it in the k is 0 sector, or I could find it in a non-zero k sector. And so let me just give you what in the k is 0 sector. This has been there's a nice result. Actually, I found this there's an honors thesis by a student of Diakonis, Nego, who's now a professor in Duke, who's written a very beautiful thesis about Markov chains and beta ansatz and Heisenberg models connecting things. And he states some rigorous results that if you take the ferromagnetic Heisenberg model in this sector, you can also relate its spectrum to the Markov process of shuffling cards. I won't go into that. I don't want to. I think people are tired out from all these things. So but there's actually a rigorous result that gives you this gap that we can invoke. But of course, now we're not done with bounding the gap, because we have to look at what is the lowest energy state in a non-zero k sector. Because I said the spectrum of the circuit Hamiltonian is the union of those. Now, if k is small, I can use rigorous perturbation theory, because if d is much larger than n, and the lowest eigenvalue of the Hamiltonians in other sectors is then 1 over d squared. But I don't think this is this is not, this is only a perturbative argument. So now, and I think this actually will work, there's a small modification of this problem where we can apply a Kitaev lemma to deal with, to lower bound this for any sector. But we will need to use the Heisenberg model, this gap, when the Heisenberg model is looked at with open boundary conditions. So there's some more work that we're doing, and what I want to finish by is, well, you could say, well, why am I doing? Because it looks like this is a hard math problem. Maybe I've been not clever enough, or my students not been clever enough, but it's interesting though. So, and I think we have made a lot of progress on this. I just want to say something about what we expect. So what would you expect? Well, I just want to present this picture. If in terms of, diffusion, how things, not in terms of a gap, well, gap relates to a diffusion, maybe modulo log factors and so on, but let's not worry about this. So if you look, you can see it as sort of two decoupled processes, which is not quite right, but one process moves this boundary point, this h, that's just diffusion on a 1D line. So if this is d, that takes order d squared time. Now, at the same time, now of course in a constant fraction of all configuration, this boundary point can move. Sometimes it cannot move because it's part of, it has to be part of these kinks, otherwise it can't move. But that's just a constant. So that just has some constant slowdown when it can move. Now, if you fix this boundary point, you can ask how quickly do you explore all possible shapes of this string, all possible configurations. Now, that is determined by this Heisenberg gap, which is 1 over n squared. So, and of course, you want to be doing both. So in order to explore the whole space, right, this mixing relates to, if I start with a configuration, how many times do I get uniform samples from any, with equal probability I can get to I have any configuration. So we need to do this, we can only make one move per step. So we either do that or we mix there. So we'd expect something like 1 over n squared d squared. And I have an upper bound on the gap from a particular excited state, which exactly has that energy. So you say, well, I was interested in seeing the effect of the locality on the and the geometric locality and the depth on the circuit, and what I get is maybe a gap that just scales like the size, 1 over the square of the size of the circuit. But I think that's because I look at when the whole thing mixes, but you could also ask, well, if I want to read out the qubit here, I only care that, I don't have to have finished the whole circuit. So there are modified questions where there may be modified models where you actually get faster mixing or a larger gap, but, it requires a modification. Okay, so, well, this was a little bit of a risky talk in the sense that I cannot claim that I've completely solved the problem, but I think it's sufficiently interesting to actually talk about this, and maybe some people have some suggestions or feedback on this. One thing that we definitely, aside from this Kitaev lemma, which I have, that I'm pretty confident that we can make this work. But there's also, at some point in my talk, I said we put on periodic boundary conditions in time. This is actually problematic for QMA. So if I really want to get a QMA result, I have to show how the gaps that I get for the translation invariant model relate back to the non-translation invariant model. And of course, you can always say, well, it's just a boundary effect, and the ground state and excited states are very delocalized, so they feel this very small, etc. But of course, this is not a mathematical proof of anything. No. The translation invariant model has these pure light configurations. But for QMA, for quantum random walks, this may not be a problem because, like I said, there is this Nagaches has shown also how you do quantum random walks on a circle. So you can have periodic boundary conditions. Now, I didn't talk about, we have other parts of our QMA proof that relate to this model that are all done. So it's this gap bound that's really the non-trivial step. Now, you can also, of course, if you like this model and the math that comes out of it, you say, well, you could look at a two-dimensional quantum circuit. Then I have a membrane that's propagating. Or I could have a circuit with very high connectivity where every qubit can interact with any other qubit. And what do I get then? So this, okay, so that's, I'd like to stop there.
Okay, questions? We have some time, so.
5 minutes.
Yeah.
Yeah. Charlie, yeah?
Maybe you can explain a little bit more of the relation of this to the Feynman's original suggestion, where you had this Hamiltonian and then you gave the initial state in the form of a wave packet that propagated through.
Yeah, and I think you can do the same thing you could do with this depth clock, I think. So this model, so if you look at this, I define a register H. That's a clock. And I'd like to put that into, well, maybe I put these spins in some initial state, and I put this clock in initial state. And I can imagine, that's this Hamiltonian is just hopping model, but of course it is coupled to this other part. So that is where it's not quite the same. But you can imagine that you put a wave packet in there and you propagate it forward, that you would find it with high probability somewhere over there after time d. But the thing is that you would not, that doesn't mean that you've explored every configuration, that you've done all the gates. It's more like maybe you've done the past causal cone of that qubit that corresponds to that point. But that I don't really, I mean that's what I expect, but I don't really know. But there is another, the Wiesel model has a similar thing where you have the fermions, they could start all, and there's, for every fermionic track corresponding to a qubit, you have a little wave packet. And but you have to synchronize them. And they all go into the circuit and have to sort of scatter and then go out. And then their internal state would be the output state of the quantum circuit. Okay, Frank had first a question, yeah.
So what is it? So this is a one-dimensional model at the end, no?
No, this is one-dimensional coupled to a counter. So it's a Heisenberg model where only the boundary term is coupled to some d-dimensional register. And so I can put the d-dimensional register in eigenstates, they're very simple in this model, and then I just get the spectrum of indeed one-dimensional chains that are labeled by k, by the momentum of this clock.
Does that mean that this is something like a transfer matrix? Is that a transfer matrix, or what is that object?
I don't see why it's
Well, yeah.
I don't understand what
Why
you
is it
mean
one-dimensional?
This model is just representing the dynamics on this. If I fix this H, yeah, it's just determining the dynamics on this of this string. Yeah. So the string I characterize by a sequence of pluses and minuses, which are like go that way or go that way, go that way. There's a certain dynamics on that.
But the length is
That's the Heisenberg.
But the length is not fixed, no? What is it?
The length, what do you mean the length? This wraps around on the cylinder.
Yeah, then it's fixed.
Oh, sorry. And yeah. So I just have equal number of upspins and downspins.
Yeah, indeed.
And it's just when the two spins, the Heisenberg model does that. I just do these flips. The Heisenberg model, this Fermi, it's just permutations. Yeah. Okay. Aaron?
Can you have different numbers, different sectors corresponding to different winding numbers that have that leads to difficulties in having this mix?
No, because I just have the strings. They have to wrap back. I put a periodic boundary condition here. So a proper time configuration is one only where the times are always, either the same or one off and one different.
Does the clock register wrap around?
Well, there's two things. There's this clock. If I put in periodic conditions in time, that wraps around.
Yeah.
But there is already, so it's a cylinder in this direction. That I can do. That's just corresponding to that my original 1D circuit was on a line, was on a circle. Yeah. Okay. Sorry, James.
Yeah. So I wanted to ask. In the beginning, you were talking about the Wiesel model, and you always mentioned that they use fermions. Is there something special about the antisymmetry, or would it work the same way?
No, actually in their model, you can map it onto spins right away. Although it's a 2D fermionic model, it's it's very simple to make it a local 2D model. Because it's actually their models, so they have, okay, so I said they have per qubit in the original circuit, they have a fermion that's hopping and it has an internal state. So that's the spin state. And I could represent that as a track on which it's hopping. And the track is two ways, one is spin up, spin down. And the fermion never gets off the track. And it's sort of, it's more 1D-ish than the usual 2D model where you also have fermion hopping the other way. Right? You could have fermion hop that way and that way.
Would it be the same with bosons?
Sorry?
Would it be the same with bosons?
Well, you have, I don't know. Well, you don't have just two states. I think the fermions are convenient because you have the spin degree of freedom that you represent. I haven't thought about that.
Quick question, just to understand it better. So these 2 points, can I just think of this axis as height, just that we have the same?
This axis here,
Yeah, we'll call it. Yeah, exactly.
yeah.
We'll call it a height.
the depth or whatever. Yeah.
So top and bottom have the same height because it wraps around.
Yes, I identify D with 0. Yes.
Perfect. And these walks, can they ever get behind the top and bottom?
Yeah, but if I have this periodic, they can get all the way. They can go like this, and then they go there. Yeah, of course now that doesn't close, so that's not the proper, right? Because I have to get it to close in this way. I cannot have something like this goes like this goes like there, and it continues like there. That's not, because then I have every.
Yeah. So if you
It does never winds around twice over the cylinder.
Oh,
That's
sure.
it.
So if you
That would
start
be
like-
like a
Two double
combination
time.
with closed time-like curves or something.
Well, I'd like every qubit has two different times. I don't know what that would mean.
But when you evolve, doesn't it just propagate to the right?
Yes, but also propagate to the left because you can undo gate, right? This can go to there. It's the Hamiltonian has the Hermitian conjugate. It has both ways.
So the only constraint that you have is for these two.
Well, I've now written it as something where I have this boundary point, which sometimes moves, and the rest is also just fluctuating. It's a fluctuating string.
So
Sorry.
let's go.
Now it goes out of.
One more question from Beth.
Yeah, I just way in the beginning you had some brief statement about some work where the gap was based on the hopping Hamiltonian, and that you said somehow that you didn't believe that.
No, the Mizel. So this Mizel, yes. Okay, so they introduced their model, and I want to understand their model, and I wanted to express it into this regular qubits, and I want to understand why they thought it was good for QMA. They state the gap, but I just don't understand the proof. I can't believe the proof. It's very short, and I want to understand this better. They say it's 1 over, I think, n to the third or something.
Because the hopping Hamiltonian.
No, but it's not just a hopping Hamiltonian.
That
it's the
was my
whole
question.
string thing. So that's why I don't believe they solved this problem rigorously mathematically, because it's not actually that easy. So that's the thing. No, the hopping Hamiltonian is the original Kitaev Hamiltonian with one clock for everybody, and that's a very simple spectrum. Yeah. But if you want to keep more details with the original circuit, what you see is you have to bound a much harder, the gap of a much harder model, but still, has some interest, I think. Yeah.
Okay, then let's thank Prof again.